So good afternoon. Good to see that a few people found their way here. It was not so easy. So my name is Joonas Govenius. I'm the CEO of a company called Arctic Instruments. So we spun out this company about a year ago, commercializing parametric amplifiers. That's basically what you need in order to to do a qubit readout in superconducting quantum computers. We are a recent company, but in fact, we've been working on these amplifiers for many years already in my research team before spinning out the company. So I'll say a few words about just my perspective on the need to scale up quantum computers, and then a few words about how you read out qubits in superconducting quantum computers, and then some of the issues we will face with scaling up those solutions. So what I'm showing here is a slightly simplified version of a graph that's actually from this recent paper by IBM, where what you can see are these applications, kind of known applications, or maybe I should say relatively well-known applications of quantum computing, which are like quantum chemistry and cryptography. In particular, they are shown as these areas in shades of gray here. And then on the other hand, what you have here are these like baseball field kind of shapes, which indicate sort of the accessible region for a certain number of qubits that you could reach. So if you have like 5,000 physical qubits, you can access sort of this region. If you had 50,000, you could access this, and if you had like 500,000, then you could get up here. And of course, it depends on the sort of the error rates you have. Here I'm assuming that you have like 99.99% gate fidelity, which is it's a bit more than what we have now, but it's only sort of one order of magnitude more than what we have now. So I think it's not like a pipe dream. I think we'll get there in a few years, not like decades. And then, it depends on details of how you do the error correction. So here I'm kind of taking the optimistic assumption of that people will be able to implement these so-called gross codes, which IBM is now advocating for quite strongly, which kind of reduce these numbers by roughly one order of magnitude at the expense of making it a lot harder to achieve that connectivity between the qubits there. The main point here is that it's obvious that we'll need very large machines, I think, to really get to these known applications. Of course, I hope, and probably all of us hope, that some smart theorist will come up with very ingenious algorithms that can achieve something useful down here, and I think it's possible. We've seen examples of these kind of algorithmic breakthroughs in the past, including these codes for doing error correction. But I think, in my view, the point is that even if we do find such applications, it won't remove the desire to go to much bigger machines. It's like, if you think of classical computers, in the 70s we had like people had, I wasn't born, people had the first transistor-based calculators, and people didn't decide that, okay, that's enough, let's stop development. And I think we haven't seen that day yet, that sort of the software and applications people would say that, okay, we have enough computing power, don't worry about making better machines. So I think exactly the same will apply here anyway with the quantum computers as well. Right, so so then what's the implication for readout? So to explain that, I'll I'll, on a very brief level, try to explain how you actually do qubit readout with superconducting quantum computers. So that's shown in this diagram. In this dashed box, we have a qubit here. It's this Josephson junction and a capacitor. And then the way you measure essentially universally in these systems the qubits is that you send in a very weak microwave signal. It interacts with the qubit, and then what comes out encodes the information about whether the qubit is a 0 or 1, like the phase or amplitude of that microwave signal tells you whether it's a 0 or 1. Then you have all these components, including a very sensitive microwave amplifier, which you need because it's a very weak microwave signal you send in. So you need a very good amplifier, very low noise amplifier to read this out with high fidelity so that you don't get errors, that you can get your 99.9 or 99 fidelity for the readout. The good news is that you can do what's called frequency multiplexing. So you can use one amplifier to read out, let's say, 5 to 10 qubits. So you don't need quite as many amplifiers as qubits, but you do still need a lot of amplifiers. So if you want to have 10,000 qubits, you're probably going to need at least 1,000 of these amplifiers. And yeah, so the amplifier part itself, I think now we, at this company Arctic Instruments, we have it sort of solved in the sense of reproducibility. We can make the amplifiers. But now if you take a very kind of a practical look at this in terms of just the weight of these components, you can start adding up just how much these weigh. So the amplifier itself is very light. The one we make is very compact, so it's only 30 grams, so that's like a chocolate bar, a small one. But then you have all these auxiliary components. You have these so-called isolators, then you have a few filters, which are all like 100 grams. And then you have magnetic shielding, you have cabling, you have some pieces of copper just to put everything together and thermalize everything. So actually, when you add all these up, you get something like closer to a kilogram. So let's say 1 to 2 pounds per amplifier, right? So this is that's a problem, right? If you now have 1,000 of these, it's going to weigh like the size of a small European car, right? So maybe you can cool that down to 10 or 30 millikelvin. If you buy the fanciest fridge from Blue Force, you might just be able to do it, but it's really pushing it. And clearly, then if you go 1 order of magnitude more, you're not going to be able to do it. So what can we do? Well, so the answer is naturally that we need to integrate more of these components instead of having these discrete components, which all weigh 100 grams with separate packages like this and cables in between. We need to start integrating them. And we have already now, we're just about to release this new version of our amplifier, which integrates this component, which is a so-called pump coupler. I won't go into detail on what it is. But it already simplifies the situation quite a bit. So going from this mess here, you already simplified a lot. However, you still have these discrete components and the supporting infra here. So what the next step is then is to integrate these other components, these isolators, and that's a much harder technical challenge, but I think we will have to do it. Once you do that, then I think you could maybe get this down to something like 100 grams ballpark for all of these components. However, if you still have this separate package with these connectors and cables, you're still going to need these kind of overheads here, like the cables and the mechanical supports. So really what you need to go for ultimately is like direct integration with the quantum processing unit itself. And that's maybe where it also gets interesting from like the broader industry perspective, in a sense, is that, I mean, up to this point, this is something we could in principle do at Arctic Instruments or a similar company alone, working on just the amplifier. But then here it changes, right? So we need to be working closely together with the IBMs and Googles, et cetera, all these quantum computer manufacturers to have that interface, both the physical interface and the electrical interface, sorted out. And this is, of course, how classical computers work. So you buy a motherboard with a certain chipset, and the memory or the hard drive doesn't have to come necessarily from the same manufacturer as the CPU. So that's, I think, then ultimately what we'll need, and then we get to kind of, then we can cross out these ones, and then we go from the situation where this readout chain is actually the heaviest part of the system to the situation where it's no longer the dominant part of the system size or weight. Yeah. Right. So yeah, in summary, my point was that we will need a lot of qubits, or we will want a lot of qubits. And currently we're measuring the weight of these readout solutions like in pounds per readout channel. I think we can go to 1,000 qubits, no problem, with just brute forcing the existing solution. But ultimately, we do need to eliminate these separate packages, go for this integration directly with the QPU. And then I would end it on a positive note to say that I think this can be done. It's not I think this will not, it's a very challenging problem for sure, but I think this is not going to be the showstopper for quantum computing. So I think this can be done. Yeah. So thank you.